Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss about oscillators. Already we have discussed in the previous video about RC oscillator. R and C elements will be present in the feedback of the oscillator and hence it is called RC oscillator. One example of RC oscillator was also explained, that is RC phase shift oscillator. In RC phase shift oscillator, we had three pairs of RC elements in the feedback path and thus it generated a sinusoidal waveform. Another kind of RC oscillator is Wien bridge oscillator. Okay. In today's video, we are going to discuss about LC oscillators. LC oscillators means we have inductor and capacitor in the feedback path that is responsible to generate high frequency signals. These kinds of oscillators are otherwise called as RF oscillators because they are possible of generating radio frequency signals. This circuit contains an LC tuned, LC resonant or tank circuit in the feedback path. By using the practical values of capacitors and inductors, it is possible to generate high range frequencies like greater than 500 megahertz of frequencies are possible to be generated. These oscillators are used in heating with high frequency, radio frequency generators, radios, TV receivers, etc. So in LC oscillators, there are two types which are commonly used. They are called Hartley oscillator and the other one is Colpitts. So these two are best examples for LC kind of oscillators which has LNC components in its feedback path. The frequency generated by these kinds of oscillators are 1 by 2 pi root LC. So based on the component values, reactance values of XL and XC, they are classified as Hartley and Colpitts oscillator based on the placement of L and C. Yes, next we will move on to draw the circuit diagram of Hartley oscillator. Hartley oscillator is a kind of LC oscillator. The basic biasing of voltage divider biasing with R1 and R2 resistors are given. We know that oscillators do not need an input signal directly, and output signal is generated by the presence of the elements connected in the feedback path. Usually we will have a RC resistor connected to the collector terminal, isn't it? Here we are replacing the resistor by an inductor. To the collector terminal, the output capacitor is connected. That is, a fraction of it has a capacitor in parallel with inductor. The inductor is connected with the center tapped grounding. A capacitor C, L1 and L2 with L1 and L2 with the grounding in such a manner. And you will be collecting the output here. And this is the feedback path. The feedback path is taken and connected to the base of the transistor. Yes, we have our E resistor and a CE capacitor. Here, a plus VCC. So, the portion of the circuit connected here is a pair of L and C, while L has two components of L1 and L2, both of them with their center tapping. This circuit is called LC circuit or tank circuit or resonance circuit. So as soon as plus VCC supply is given, the biasing of the transistor happens, and with the presence of the components with suitable values of ratings, the circuit is capable of generating a sinusoidal wave whose frequency will be greater than 500 megahertz of frequency. So here the value of ff is equal to 1 by 2 pi. 2 L's we have ascended, it is L1 plus L2 into C. This is the frequency of the signal which is generated by the Hartley oscillator. Yes. The next type of oscillator is Armstrong oscillator. This is otherwise called as Meissner oscillator. This is just a small transformation of the previous Hartley oscillator. We will be doing that circuit now. Here also the RC is replaced by a choke which enhances the signal. Output capacitor, the other capacitor grounded, the emitter with the output capacitor, the coupling capacitor, C, B, and E. RE is the emitter resistor, C is the emitter capacitor, R1 and R2 are the voltage divider biasing circuits. Yes, what do we have in the output? The main part of the LC circuit is connected in the output or the across the capacitor. Yes, L1 and L2 with mutual inductance with this manner. The output of the L2 inductor is connected to the input of the transistor. So mutual inductance happens between the two coils L1 and L2, thus acting as a transformer section, L1 being the primary and L2 being the secondary. So beta is the feedback fraction, mutual inductance divided by the inductance of the circuit, as the gain, if the gain is greater than 1 by beta, beta is the feedback ratio, it is given by L by M. So the minimum gain A minimum is equal to L by M. Frequency of R is equal to 1 by 2 pi LC. Yes, this is about Armstrong oscillator or the Meissner oscillator. The radio frequency choke present in the capacitor enhances the signal. CC capacitors behave as blocking capacitors which blocks the DC and allows the AC component to pass through it. We are moving into another important kind of device called UJT. UJT, the full form for UJT is uni-junction transistor. I'll be drawing the configuration of this UJT, uni-junction transistor. So we have three terminals for uni-junction transistor. I'll be showing it right now. Yes, the terminals are base 1, base 2, and emitter. This is the emitter terminal. The supply voltage VE, and this is the voltage given across base 1 and base 2. P channel and a larger area of N channel. So IE current passes through this. As the supply is given, the charge carriers displace with majority carriers of positive charges present in the p layer tries to move into the holes of the n channel. The circuit diagram of UJT, that is the equivalent circuit diagram for the UJT, is now being drawn so that we will be able to understand. Yes, so this is RB2, RB1 and emitter voltage plus minus. IE current, emitter current flows through the simple diode. The voltage across the diode it forward biases and a net voltage potential is felt across the voltage divider point across RB1 and RB2. If the value of the resistance is varied, then eta VBB will also vary. When the value of voltage across the emitter and current is varied, we will be getting a typical graph in this manner, taking IE on the x-axis and VE on the y-axis and varying VBB having constant value. The VE increases after reaching a maximum point. The curve increases in this manner. I will draw the curve again. As the value of IE increases with constant VBB, the curve increases, reaches a peak value, and it increases like this. This value of voltage is called valley voltage because this voltage, this portion of the curve looks like a valley, and this voltage is the peak value. It's called the peak value of voltage. Yes. So when it is drawn across the x-axis, it is peak current, and when it is drawn across voltage, it is valley current. So now this point is called the valley voltage, and this value is called the peak value. Yes. So this region is called the cutoff region. This region is called the cutoff region. This region is called negative resistance region. Negative resistance region, and the region above the valley point is called saturation region. Yes. So when a value of voltage is first applied, the unijunction transistor is off and the capacitor C1 will be fully discharged but begins to charge up exponentially through the R3 resistor. As the emitter of the UJT is connected to the capacitor, when the charging voltage VC across the capacitor becomes greater than the diode volt drop value, the PN junction behaves as a normal diode and it becomes forward bias, triggering the UJT into conduction. The unijunction transistor is on now. When the voltage across the capacitor decreases below the holding point of the PN junction, the UJT turns off and no current will be flowing into the emitter junction. So once again the capacitor charges up through resistor R3. Now the important application of UJT is it is basically used as a relaxation oscillator because of the construction of UJT is in such a way it is used as a relaxation oscillator where the voltage increases, reaches a point and sweeps away the voltage. Yes. The emitter is connected here, and we will try to name the emitter terminal phase 1, phase 2 of the UJT, R1, R2 resistor, R3 resistor, C1 capacitor. So the output is taken across VB1 and VB2. Yes, so two outputs are possible when the DC voltage is given plus VCC voltage is given. This is at a ground potential 0 volts. When plus VCC voltage is given, on top of source voltage, constant voltage. When it is given, the charging of the capacitor happens and thus the emitter turns on, and for a particular time period. Initially, the output voltage remains at 0 initially, and then it reaches a maximum point, falls down, reaches a maximum point and falls down. This is because of the charging and the discharging of the capacitor, as we discussed, the voltage across the capacitor. This minimum space is called the V off region, and this is the on region. Yes, this is the V on and V off. So this is the sweeping of the voltage, and which is nothing but the capacitor voltage. So at time t is equal to tau, tau is equal to R3 into C. This is a time constant tau. And proportionally, when there is an increase in this voltage, the VB2 value increases and then decreases. Again, VB2 value increases and then decreases. VB2 for a particular time t. Yes, so voltage across VB1. Similarly, VB2 also realizes the same value of the voltage. So this charging and discharging process between V on and V off is constantly repeated while there is a supply voltage Vs, which means that as long as the supply voltage is given, this sweeping of the output voltage waveforms are obtained. So this kind of voltages are applied to turn on semiconductor devices like thyristor family devices like SCRs. So it is an important relaxation oscillator which is used for triggering the switches of the thyristor family. So in today's video, we have discussed LC oscillators. There are two types of LC oscillators, Hartley oscillator and Colpitts oscillator. In Hartley oscillator, the tank circuit, that is, the capacitor and the inductors are connected in the feedback path in parallel. The inductors are connected with in such a way that two inductors are center tap grounded. In Colpitts oscillator, the same manner, capacitor and inductors are connected in parallel with the feedback circuit, but two capacitors and one inductors are used. These two capacitors are connected with their center tapping grounding in parallel with a single inductor. So the value of the frequency generated in LC oscillators are greater than 500 megahertz. Another example as Armstrong oscillator and UJT relaxation oscillator we have discussed in today's video. Thank you.